formulas are what we're going to be using now to calculate Z, which is darn close to what you described. I want to make sure you understand this formula that we learned last week, because this week you're literally using it. That is step 4. Let me, real quick, I want to read these, and then I'm going to talk about step 4 in detail. Draw a number line with a bell curve above it. 2, use the information below to label the number lines, the mean, and the 6 numbers. You know, at this point, yes, keep showing a little work. Look, I'm showing the work right here. Matter of fact, I'm doing this. This happens to be the rent. Remember that rent problem? Let me go back. Whoop, whoop. Remember all these rents? Here they are. Look at all those rents. I went ahead and said, and got the mean off of here, which is way back here on slide 8. There's the mean, 490.80. And then on slide, I think slide 33, the standard deviation is 54.74. So that first step where it says draw a bell curve, a number line with a bell curve above it, it's just like this. The second step says label the mean and the 3 numbers above and below. Show some work that you're adding and subtracting the standard deviation to get these numbers. There it is. The third step says, again, I'm trying to remember. Step 3 says shade the bell curve area above the number line that represents the probability of X being asked for in the question below, okay? Use the Z equation, here it is, X minus the mean, then divide by the standard deviation to calculate your Z statistic information from the information below. Explain which Z chart you use, the positive or the negative. I want to make sure you realize what that is. This is the negative Z chart. Down below is the positive Z chart. Anytime our Z calculates on the number line from 0 to positive 3, we're using the positive Z chart. But if our calculation comes out to 0 to negative 3, we're using the negative Z chart. It says, tell which Z chart, positive or negative, and look up your calculated Z stat. So let's hypothetically pretend like this problem ended up being our problem. And we know it's supposed to be 92.72, but we manually calculated Z this time, and we got plus 2.0. So we go to the positive 2.0 Z chart, and we would say, using positive Z chart, we look up 2.0. Oh my gosh, don't forget which column we gotta use. 2.00 means we gotta use this first column, because the second digit is 0. So we're gonna not be able to see it. Oh, can we see it? We can see it. There it is, 2.0. There's your answer, just to the right of my cursor there. 0.9772. 0.9772. There it is. That's what we're doing on the homework now. You're going to show your work to calculate that Z, just like we did. Pretend like I got it too, and then you look it up and you write it down. Here's the deal. I want to remind you, I mentioned this last week. This Z chart always gives you the probability of any number on the number line to the left. So if I'm asking a question, what's the probability of this or less, you're getting it off the Z chart, negative or positive. But if the question says, what's the probability of this blah, blah, blah number or more, you have one extra step. That's the part you need to remember. You're getting the number off the chart, and then you're subtracting it from 1. That's the extra step if it says more than. All right, you ready? What am I going to do here? You know what? I'm going right here. I want to do these. Listen, I want to remember the formula again. The number being asked about minus the mean divided by the standard deviation. But I want to give you a heads up. Again, this is coming in our future. This isn't for this assignment. Coming for our future, the formula is going to change slightly. It's not just divided by the standard deviation, it's divided by the standard deviation over the square root of the number in our sample. Right now, our sample size is 1. Week 1, our sample size is 1. Week 2, our sample size is 1. Week 3, our sample size is 1. If you divide by the square root of 1, it's just 1. So all you have left is the standard deviation. That's why we're using this formula right now, because our sample size is only 1. All right, everybody see that? Okay.
Professor?
Yes.
I actually just remembered, the dividing by 2, that's like question was 70.6 minus that mean divided by the standard deviation, which
Would have given you a 2 then.
I think so.
Yeah.
Something like that.
Yeah, that's what you have to do this week. That's what you have to do this week, exactly what you did last week.
Yeah.
And then you gotta look up the 2. All right, we're gonna practice this now. Here we go. Look at the reds up here. Here's the number line based on the standard deviation. Within 3 standard deviations above and below, we gotta be within, I'm gonna round to the closest dollar, $327. So let me just put that in big letters here so everybody can see it in the back. All the way up, I'm gonna round to 655. There's our range there. Are you ready? Give me a rent between those 2 numbers. Just give me a hypothetical, not any number you see up there, don't give it to me. Give me just one that pops in your head. Between those 2 numbers. 400 even? Okay, $400. We're being asked about what's the probability that we have 70 pieces of paper here with the rents, all those 70 rents written on them. Just like this. Oh, come on. Boom, there they are. And 400. Wait a minute, let me go back up here. Oh. Right there. Okay, there they are. There's all the rents. I have all 70 of them on a piece of paper. Here's the question. The quiz will say, the mean of this data is $490.80. The standard deviation is $54.74. What's the probability you draw one of those 70 rents out of the hat and it's $400, it says $400 or less. $400 or less. There's the formula. $400 minus the mean, 490.80, divided by the standard deviation, 54.74 equals Z. Z gonna be positive or negative? Can't hear you. Quit. Stop. Negative. Look at 400 minus 490. This is pretty easy. This is negative 90.80 divided by 54.74 equals. That's 1 point something. 1.6 what?
1.6587.
Stop there. We only have to go 2 digits because our Z-chart will only go 2 digits. When we drop the Z-chart, we're a couple of weeks away from getting rid of the Z-chart, and we're only going to use Excel to calculate these. But while we have the Z-chart, we only need to go 2 digits on our Z to the right. So give me it to 2 digits with the proper rounding. 1 point.
1.66.
Oh, quit. What's the next digit after that 6?
1.658.
Oh, good call. Okay. Yeah, I thought I had you there. Negative 1.66. There's the Z. Now we look it up. This would be the probability of us drawing one out of those 70, and it's $400 or less. You know, we get the negative Z chart. So as I'm writing down my answer, I'm showing my calculation, negative Z chart. Because you gotta tell me for this first assignment which Z chart you're using. So, you know, I know you're going, gosh, why do I have to write this down? 1.66, so don't forget, we're using the column. The second digit is a 6, so we're using a column right here where the 6 is. I'm going down to negative 0.16. There it is, just to the right of my pointer, just to the left of my pointer. How's that? I see 0.04, 0.0485. Is that correct?
Yes.
0.0485. Leave it just like that, and that's your answer for 400 less. But some of you are going, I want to turn it to a percentage. So I'm moving the decimal 2 places, 4.85, and add the percent symbol. Ugh. Add one better than mine. How's that? 4.85%, which makes sense because look at where 400 lands on this number line. It's way down here in the tail. So just that little bit right there would be just slightly less than 5%. So it makes sense. Let's pretend that came out to 5%. What's the probability then of us picking one out of a hat and it's $400 in rent or more?
95.
I heard it.
95%.
Thank you. 95%. The opposite of 5%. That's the only extra step you gotta do for the more than. You guys gotta find the opposite. 100% minus the 5%, if that were 5. That's it. Oh my gosh, this is too easy. You guys thought you hated stats, and we still do, don't forget. But now we find it easy, right? Let's do another one. Hang on, man, let me stare at this for a minute. Between $327 and $655, give me a rent. 500, we're going 500 now. Here's the formula, whatever is being asked about, the test says, hey, we have 70 pieces of data and the mean of these rents in this data is $490.80. The standard deviation is 54.74. You're about to draw one out of the hat of 70 pieces of data. What's the probability that one you just drawn out was 500 or more? Or more this time, not less. 500 or more. What are we being asked about? We're not being asked about the mean. We're not being asked about the standard deviation. We're being asked about $500. The formula says whatever you're being asked about minus the mean, parentheses, because you must do that subtraction before you divide. So here we go. 500 minus 490.80. This is going to be easy. Divided by 54.74. 500 minus 490.80 is going to be, that's $9.20, I think. Does that sound right? Divided by, oh, this is such a low number. Equals. So 500 lands about, gosh, right there. Okay, without me finishing this calculation, look at where it lands. Hang on, let me put this pen right here. I'm going to put it like a little, there. Nice big dot there. The answer is, what's the probability of 500 or more? Our answer should be darn close to what percent? Because look where that dot lands. 50%. Our answer should be darn close to 50% because that dot where 500 is just on the right side of the mean by a little bit. So if we do these calculations correctly and we remember to do that last step to subtract from 100 to find the opposite, and our answer is around 48 or 47 or 46 or somewhere in there, 45 even, we can feel confident we probably did it right and move on to the next problem. That's what the empirical rule does for us. It allows us to have an estimate before we even calculate this so we don't have to double check ourselves and move on to the next problem. Because don't forget, you know what a week from today is, right? Wait, I don't see everybody like knowing exactly what a week from today is. Oh, okay, just making sure. All right.
Wait, it's on. Yeah.
Week from today. That's it, boom, 7 days from now. I want you to stress out. Especially you, for missing the lecture.
I'm already stressed.
Good, you should be. All right, so where am I at? 920 divided by 54.74?
0.6.
Point
No,
oh six?
0.168.
Okay, 0.168, which means I gotta go to 0.17, because we only go 2 digits to the right. What's the digit in front of the decimal? A 0. This was positive 0.17, because we only go 2 digits to the right for the z chart. So I'm going to the positive z chart now. I'm gonna pick my column based on the second digit to the right, which is a 7, so we know we're gonna use this column way over here, where the 7 is, and then it's 0.1 is the row we're using. 0.1, there it is, just to the left of my cursor right there is our answer. Wait a minute, that doesn't make sense, does it? 0.56, what is that? 0.5675, is that what it says? Someone help me.
Yeah.
That's what it says? There it is. That doesn't make sense though. Our answer was supposed to be below 50%. What am I doing wrong?
You subtract
You didn't subtract it from 1 yet because the question says 500 or more. I haven't done that last step. That's what I can tell you right now. Somebody who's hearing my voice as we speak is going to forget to do that last step. I'm trying to remind you as much as I can, but somebody's going to forget. I can't get through to everyone every semester for some reason. Somebody says, I'm going to defy what you say. I don't believe you. 100, so 1.000 minus that. The opposite of that would be 44.4325, I think. Does that sound right? And if you want to turn it to a percentage, move the decimal 2 places, 43.25%. If I recall, I said if you get an answer around 48, 47, 46, even 45%, you're probably correct. We're at just above 43%, that's probably correct. Well, these are almost too easy, aren't they? Now, does everybody have a good feeling how to do that 4th step on the number line assignment for next week?
Which 4th step?
That 4th step on the instructions on the number line assignment. Let me show you. Again, I want to make sure you see it.
So that was the, my bad.
This is all the fourth step that you haven't had to do for homework yet for a number line assignment, that now you're putting everything you've learned on number line for the last couple weeks, putting it all together to where we're actually calculating the true percentages underneath this bell curve. No matter where the number is on that number line now, we should be able to do any number. Let's do another one, right? I wanna know, is someone willing to be honest or raise their hand and say they're not quite getting this yet and willing to admit they're not quite getting it? Okay.
I have a question, because I was lost, the Z chart didn't have a .17, we were looking at .07, including
0.1 was the row, and then we went to 7 for the column, because that's the second. So we went to 0.1 for the row. The row's always the first digit on the left of the decimal and the first digit on the right. That tells you what row. The second digit on the right tells you which column.
Did you round that up from
I did round it up because we could only use 2 digits for the Z chart, or else I would have went out 4 digits if we weren't using the Z chart. So 0.168 rounded is 0.17, so that's why I went to the 7. Anyone else feel that they want to see this one more time? You want to see it one more time? Okay, I'm going to let, since she wants to see it one more time, I'm going to let her pick any number between 327 and 655 for us to calculate that probability.
575.
She wants to do 575, 575. Let's look at this number line. Where does it land? It's way up here, close to 600. I'm gonna just guess, maybe like right around there. Now let's make this fun. Let's find the probability for less than and the probability for more than. Why not? Right? Because once we found less than, we just gotta find the opposite anyway. So let's find them both. My question is, if you had to estimate the less than, think about the empirical rule, look at where it lands. Let me draw it bigger. Here's 575, my estimate of where it might land on the number line, and if we were using the empirical rule, you know this would be greater than what number? You know the probability from that spot over to the left would be greater than what number?
60.
You know it's greater than 50%, because from here over is 50%. So look at all this other stuff we have here. Matter of fact, you see this from 490 to 545 right there? We calculated that. Where is that? That's right here. That's 34.13. So we know, since this lands outside of that first standard deviation, real close to 2 standard deviations. Matter of fact, in our homework, we calculated exactly what 2 standard deviations would be. And this falls just shy of that. So we can almost estimate what that would be to the left based on our homework, because there it is if it was from the -2 to the, from the +2, is that +2? From this +2 to the left is 97.72%. So someone tell me, what do you think it might be right there, just shy of that +2 standard deviation? Take a guess. To the left. 95, 96 out here. These are all good guesses. I'm gonna go maybe 94, right in there. Somewhere in there, because we know 97 is at 2, so just below it's gotta be a little less, right? It just makes sense. That's what the empirical rule assignment was all about, for you to be able to visualize what the answer should be now. And these calculations, you don't have to rely on your, oh, did I make a mistake in my math? You have no idea. You'll be able to, every one of these problems, if you visualize it, you'll know where your answer should be around. And then you show the math, and oh, look, it's right near what I thought it would be. And you go on to the next problem, and you know you aced it. Are we gonna get A's on this first test? You think so? You're scaring me. You weren't even here for like 2 weeks. I think it's your first class. No, where is he? I should give him a hard time. Anyway, I don't even know where he's sitting. All right. we need to do one. 575. 575 minus what? Somebody help me. That's right, 490.80, the mean again, divided by 54.74, just like all the rest. This is easy because you got 75 to 500 plus another 920. 575 plus 920, or 575 minus that. 75 plus 920 make 75, 80, 420, is that right?
Yeah.
8420 divided by 5474 is going to give us our Z. That only goes in there once, so and this is a positive 1.537 makes 54, right? Because we can only go 2 digits, so 1.54 is our Z. When we look this up on the Z chart, first of all, are we gonna look up the negative or positive Z chart?
Positive.
Positive Z chart, very good, because it's a positive 1.54. And when we look it up, are we finding our answer for $575? There's 70 rents there, we're picking a number out. We're trying to find the probability for $575 or less, or $575 or more, what we're about to look up. Less. We're about to look up less. We have to do an extra step to find more. So we're about to find what's the probability. We draw one out of the hat, and it's 575 more. We estimated it should be just a little shy of 97, maybe 94-ish, somewhere in there. Let's go to the Z chart. Positive 1.54. Here's our positive Z chart. 5.4. We're going to use the 4 column because the second digit to the right's a 4. Now the row we're using is 1.5. So I'm going right down here to the bottom, just to the left of my pointer. I got 0.93. Help me. 82. If I want to turn it to a percentage, I move the decimal 2 places, 93.82%. Look at that, we said, we think it'll be around 95, 96, maybe 94, it's just shy of 94. 93.82%. What's the probability out of these 70 rents? One I draw out of the hat is 575 or more? No, not 94. What's the opposite of 94? 6%. 6% a little bit. So you take 100% minus 93.84, and you get, let's see, hang on, 100% minus 93.82% equals, what did I say, 6.818%. Someone check my math. Is it really 6.18%? Is it really? Good. That would be 575 or more. We've just done 3 of these in a row now. Is it sinking in? It is. Oh my God, this is too easy. You guys have the building blocks. The most important things. When we get finished with this week, Thursday, we start going into binomial distribution. That's the beginning of now you're learning a bunch of new different formulas, but what you've learned up to this point has been the true building blocks of this whole class. And if you are all caught up and you feel like you're not being left behind, you're gonna be fine in this class, because everything kind of gears around this, right here. And if you understand this, you're gonna understand the rest of the semester. All right, these were the building blocks. All right, we gotta learn a couple of new things. So where are we going here? We're going to Excel. Two Excel functions we gotta learn are large and small. I mentioned them last week when we learned max and min. And I said, hey, this is gonna be a little different than max and min. So the advantage, does anybody remember what the advantage is of large and small? What's the advantage of large compared to max? Anybody remember? I didn't think anybody would, but I just want to make sure. Maximum, when you use max with Excel, it finds the largest number. So if you said max from B8 all the way to where the end of that data is, it would find the largest number. Min finds the smallest number. But large, look at how large is a little different. Equals, L-A-R-G-E, parentheses, B8 dot dot B25, comma, here's the part you gotta add, comma, you can put a 1 there, you can put a 2, you can put a 3. You're telling it, you wanna find, if you put a 1 there, you're telling Excel find the largest number, just like max. You put a 2 there at the end, you tell it to find the second largest number. You put a 3, it's the third largest number. That's the advantage of large compared to max. Max only finds the largest number. Large can find any one of the large numbers you want to find. The second, the third largest, the fourth largest. Right here, hang on. There, it's finding the second largest number. Equals L-A-R-G-E, B8, B25, comma 2. Small. Equals S-M-A-L-L, parentheses, B8 dot dot B25, comma, if you put a 1, you're telling Excel to find the smallest number, just like min. You put a 2, it's the second smallest number. 3 is the third smallest number. So right here, we're finding the second smallest number of that data by putting a comma 2 on the end. Look down here. Whoop, hey, come on. There, we're finding the equals, L-A-R-G-E, This is L8 through L25, comma 3. We're finding the third largest number of this data over here. So there's two larger numbers than 453 in this data somewhere, because we put a 3 there for the third largest. Here, this is the fifth smallest number because we put a comma 5. SMALL, parenthesis, L8 through L25, 5, comma 5. Too easy, right? We all now understand how to use large and small. A lot of times we use min and max when we're looking at data, but there's going to be times where you need to find the second largest or the second smallest. So that's why you need to know large and small. Okay, here we go. All right, we're just transitioning to chapter 5 information. And in this chapter 5 information is kind of telling you some of the names of data. That's what we're starting with in statistics. So I'm going to go ahead and tell you the easiest way to identify the difference between data that is discrete, D-I-S-C-R-E-T-E, that second box down, discrete data versus continuous data. Discrete random data versus continuous random data. These rents, let me go right there. This rent right here, this is a great example of discrete data, because discrete data are the numbers with no decimal. If all the data has no decimals, no anything to the right of the decimal, I mean, other than 0, 0, then it's discrete data. All those rents don't have pennies. It doesn't say $600.85, it just says 600. That is discrete data. Now, here's the deal, real quick. Numbers that do have decimals, that's continuous data. I want to give you a quick example. What is this data right here I'm pointing at? 2, 4, 6, 1, 3, 6, 7, 12. What kind of data?
Discrete.
This data, 2.23, 5.11, 2.0, 4.21. Look at, there's one number that could be discrete, but all the data would have to be no decimals to the right to be discrete. So this data is what? Continuous. Yes, we can all identify whether the data has decimals to the right or not, but you have to, for this first test and for the rest of the semester, be able to identify whether the data is discrete or continuous based on the description of how you're going to collect the data, what kind of data you're collecting. You got to imagine you're sitting there collecting the data and say to yourself, what would I be writing down? Would I be writing down a number called an integer with no numbers, no decimals to the right? Or would I be writing down a number with decimals sometimes, meaning I'm collecting continuous data? You ready? We have an assignment. We're all meeting on Saturday. We're gonna sit right in front of the building. We're gonna pull a bunch of chairs out. And our assignment is gonna be to count the number of cars that pass us while we're sitting there from 11 to 12 for 1 hour. And we have to do it for 5 days. All right, day 1 just went by. We counted the cars. Hypothetically, how many did we count? How many, 11?
A lot.
Oh, no, okay. Give me a number.
20.
20 cars. Day 2, we sat out front, not on the main road, by the way. I'm talking about just in front of the parking lot. Okay. How many cars did we count? Plus 20 is not a lot for that main road.
Yeah.
How many cars?
Yeah.
No, 0 on the second day. We closed?
Yeah.
Oh, man. Day 3, how many cars?
30.
30. Day 4?
7.
7. Why didn't anybody say 7.5? 28.3? Because there's no way we would see a third of a car go by us. I mean, that just isn't how it works. So we know in our mind, because we just thought about the kind of data we're collecting, that it has to be discrete, because we would never write down a number with a decimal. And that's how it's going to be quizzed. You're going to be told you're sitting in front of a building, you're counting the number of cars for 1 hour for the next 5 days. What kind of data are you collecting? You got to imagine what you're going to be writing down. Are you ready? You're at a restaurant. The restaurant's a self-serve salad restaurant. They come to the cashier, you're writing down the next 10 salads, what they weigh, because people get charged based on the weight of the salad. The scale's all set up to take the plate out of the picture. You put it at a negative based on what the plate would weigh. So if you put a plate there, it goes to 0. You put salad in it, it tells you the weight of the salad. Your job is to write down in ounces how much the next 10 salads weigh for 5 days in a row. Tell me how much one of your salads weighed, somebody? How many ounces? 7 ounces. Here's another salad. Tell me what the next salad weighed. 6.3 ounces. What's the next salad weigh?
4.
First of all, these are huge salads. By the way. That's what I let you know. I think. I mean, 7-ounce salad. I don't know if I could eat all that. 4 ounces. 4 ounces. Yes, we had a 7. We had a 4 because they don't have imagination. But we had a, I don't know what it was, 6.28. Salads are not landing right on the ounce. They're landing at between 5 and 6, 4 and 3, 2 and 1 ounces. There's going to be a whole bunch of numbers that have decimals because they're not landing right on 6 ounces, right on 7 ounces, right on 4 ounces. And that you have to be able to imagine so you can say, what kind of data are you collecting? You're going to answer. It's going to be a multiple choice. Oh, I'm just giving away this test now. Darn. You got to either circle discrete or continuous. What are you going to circle in that case would be continuous, right? All right, now I want to show you a couple more. I want to make sure you get this. Oh, okay, you ready? Shoot, no, I don't want to tell that yet. I'm coming back to that. You're calling houses and you're asking them how many dependents they put on their tax return. I don't know if you guys have ever done taxes to the point to where you had to mark down how many dependents you have, but a dependent would be someone you're providing support for. Most common is a child. Also very common is like a parent that's moved back in with you. That's happened to a lot of families I know of. That's considered a dependent because you're providing them with food now and a roof over their head, so you get a tax deduction for it. So you're the one making the call, and you're calling people and you're saying, hey, how many dependents did you put on your taxes? What kind of answers are you going to get? How many?
Like whole numbers,
Like 4, like 2, like 1, 0, 3, or just yourself, 1. I don't know. No one's going to say I have 2.2 dependents. No one's going to say I have 4.1 or 4.5 dependents. That's impossible because a dependent has to be a full human living at the house. So that's why it's discrete. Here's an example of continuous. You're having to collect data about the distance in miles from all these different homes to your store site that you're managing. But they're different homes in different locations, and it's in miles. The odds of every home being exactly 2 miles, exactly 1 mile, 3 miles are pretty slim. You're going to get 2.2 miles, 3.55 miles, 4.6 miles, 1.1 miles. You're going to get numbers between the numbers if it's in miles. So in that case, you're collecting continuous data. This is the common one. You're taking a survey, you're calling homes, and you're either marking a 1, 2, 3, or 4, but we transferred the meaning of those numbers to, you're marking a 1 if the homeowner says they do not own a pet at all. You're marking a 2 if they said they own a dog. You're marking a 3 if they say cat. You're marking 4 if they own both a dog and cat, pluralized, whatever. What kind of data you're collecting? You're collecting data 1, 2, 3, and 4. Any time are you writing down 1.2, 3.5? You're only writing down 1, 2, 3, and 4s. That's all you're writing down. Those are the only 4 options you have. And so you're collecting discrete data. Everybody get it? That's how you tell the difference. You're not going to be given numbers. You're going to be given descriptions of how data is collected, and then you got to tell me whether you're collecting discrete or continuous data. Now, one last part is whether you're collecting finite data or infinite data. Let me make sure you understand the difference, right? This example says the number of TVs sold at a store in one day, and we looked up in history, and we looked at our inventory, and the most we've ever had in stock that we could ever sell in one day is 4. And so we're going back how many days? Oh, this one doesn't tell how many days we're going back. Let's say we want to collect data from the last 100 days that we've been open. And the data we're collecting is how many TVs we sold for each day the last 100 days we were open for business. And we know we could never sell more than 4. The reason the data we're collecting, first of all, are we collecting discrete or continuous data? I heard discrete twice, so you guys see why it's discrete? We didn't sell 3.5 TVs. We didn't sell 2.25 TVs. We either sold 0 TVs, 1, 2, 3, or 4 TVs each of those days from the last 100 days that we were open. So that's why we're collecting discrete data. But the fact that we will never be marking down a 5, we'll never find a 6, we'll never find a 7 means it's finite, because there's only a certain amount of data available for our answers. It's not infinite. There's no way we'd ever find a 7 or an 8 or a 6, because we know, we're told in the story, that the most we've ever sold is 4 TVs. So we know our answers are either going to be 0, 1, 2, 3, or 4. That's the data we're collecting from each of those 100 days. That's finite discrete data. What was your question?
What's the difference, like, so what's a random variable?
Random means we're randomly selecting the 100 days maybe or something like that. That's all.
Just one day out of the 100.
Yeah, that would be a random, also collecting a random variable, just one day out of the 100. But just collecting 100 days out of, we've been open for 15 years. That's also random, that we went with the last 100 days or something.
And then like discrete random is then a finite number, so like how many total days we've been open?
No, discrete finite.
Discrete finite.
Finite would be, there's only a certain numbers we can select from that we're gonna get out of those last 100 days, because we know that we've never sold more than 4 TVs.
Okay.
But now look at infinite. This one, we're not sure. We could end up with a number like 3, 4, 7, 8, 12, 15. Let me describe this. We're sitting there and we're collecting the data from the last 100 days at this, let's say it's a restaurant or store or something, of the customers arriving each day. We have a little monitor thing on the door, and every time someone walks in, it clicks another person. They leave through a different door, so we're getting how many have arrived each day between a certain time and a certain time, okay? Think of the data you're collecting. 0 came in between 10 and 11 on 2 days ago. Now we're looking at the 3rd day. 1 person came in, 5, 10. Think about it though, we have no control how many people, no information's on there that the most we've ever had come in our store. Nothing like that is in this information. This is called infinite because we have no idea what the number is we're collecting. It could go, we could have gotten 100 people in one day during that time period for some reason. There's no other information telling us that it only could be this many people. So that's why this is, also, is this discrete or continuous? How many people walked in our store? Continuous or discrete? Discrete, because there's no way a half a person walked in. Either 2 people walked in, or 10 people, or 100 people, but no way 100.75 people walked in, right? All right, that's all I wanted to get out as far as data. We're gonna get into quantitative and qualitative, I think, on Thursday. But discrete, continuous, finite, and infinite, I wanted to make sure you have. I do have, what are we doing on time? I do have a life lesson for the week.